Okay, so let's start with the topic, which is let's just start with the topic which is called as fast Fourier transforms. Fast Fourier transform. It's also called as FFTs. Okay, a lot of use for this fast Fourier transform because of because of reduced computations. Okay, so FFTs are nothing but same as your DFTs. FFT is same as DFT. Only thing is the way you calculate it. It's just a rearrangement of your mathematical expression, and that actually is actually, that's why it's called as a FFT. But the formula remains same. So how you have, let's say, for a endpoint DFT or FFT, endpoint DFT or FFT, the formula will be same. Okay, that is x of k is equal to summation n equal to 0 to n minus 1 x of n into w k n of n, where k is from 0 less than equal to k less than equal to n minus 1. Okay, so this is the endpoint DFT formula. So now if you look at it, right, in the if you just closely look at this, you have basically if x of n is complex, if x of n is complex, right, then what will happen is x of k. So let's just say x of n is complex and its value is that's fine. So x of k will become n equal to 0 to n minus 1. Okay, x of n will have a real part of x of n, okay, and plus j into imaginary part of x of n. Okay, so this is what you have. This is multiplied by wkn of n. Your wkn of n is again a complex number, right? This is actually cos of 2 pi k n over n plus j or minus j sine of 2 pi k n over n, right? This is what you have. So now when you multiply these two terms, what you get is summation n equal to 0 to n minus 1, okay, a real part of x of n, okay, into cos of 2 pi k n over n, okay, plus summation n equal to 0 to n minus 1, okay, imaginary part of x of n into sine of 2 pi k n over n, right? Now plus the same thing, what you have is j into summation k equal to 0 to n minus 1, n equal to 0 to n minus 1, imaginary part of x of n into cos of 2 pi k n over n, okay, minus plus, this is a minus, right here, this is minus plus real part of this is minus plus summation n equal to 0 to n minus 1, real part of x of n. Yes, so this is a plus, sorry, this is a plus and this is a minus. Okay, so this is a minus real part of x of n into sine of 2 pi k n over n. Okay, so this is what you get. So if you see, this is one multiplication, this is second, this is third, and this is fourth. So you have 4 multiplications happening in one iterations. Multiplication for multiplication for one iteration of n. Okay, iteration of n. Okay, so same way, if you see this, right, here there are n iterations, here there are n iterations, because you are going to multiply x of 0 into cos of 0, cos of 2 pi k n equal to 0, right, cos of x of 1 into cos of 2 pi k by n, and so on, right. So you will have n multiplications here, n multiplications here, n multiplications here, and n multiplications here. So basically for one value of k, you have 4n real multiplications. Okay, multiplications. When I say real multiplications, although this part is your complex number, but this multiplication is of real numbers, right. We have started with the assumption that x of n is complex, and then we are saying that this is a real multiplication, this is a real multiplication, this is real and this is real, but this is a part of a complex value, right. So same way, how many k values are there? K n values are there, right. K changes from 0 less than equal to k less than equal to n minus 1. So what will happen is there will be 4n into n multiplications. It is 4n square multiplications to calculate the n point DFT. Okay, now the same thing, this is one, this is the first point. Okay, for an n point DFT there are 4n square multiplications. The second point is additions. Okay, addition is, if you see, I am multiplying these two numbers and I am adding it, right. So how many additions when you do a summation n equal to 0 to n minus 1 x of n, real part of x of n, into cos of 2 pi k n over n. Okay, I am adding 1 plus 2 plus 3 plus n minus 0 plus 1 plus 2 plus n minus. So total n numbers I am adding. Okay, I am adding n numbers. So what will happen is, I am adding n numbers. The number of addition operations is n minus 1 additions. N minus 1 additions for one of this summation, right. So how many summations are there? So I will have n minus 1 additions here, n minus 1 additions here, n minus 1 additions here, and n minus 1 additions here, right. So then after this n minus 1 additions, I have 1, 2, 3 additions here again, right. So first of all there will be n minus 1, 4 into n minus 1 additions which will cover the summation n equal to 0 to n minus 1. Okay, and then there are 4 of this, right. There are 4, like 1, 2, 3 and 4. I got to add that, so that makes it like, if you see, this will get added together and this will be added together. So 1 here and 1 here, because this is a complex number, so this will be the complex, only one addition here and one addition here. So there will be 2 additions. Okay, so plus 2 additions, one real side and one the complex side. Okay, the imaginary side, one imaginary side, that is one of this here, imaginary part of it, and one here which is the real part of it. Okay, so if you add these two, so I will have 4 into n, 4n minus 4 plus 2, so that makes it 4n minus 2 additions to calculate one value of k. So same way there are n values of k, right. When I am calculating n point DFT, I have to calculate n values. So what will happen is, total will be n into 4n minus 2 additions will be involved to calculate your n point DFT. So this is the second finding that you have. Okay, this is the second finding that you have when you are doing your DFT calculations. So if you go the conventional route of having this formula, even this is true for the matrix part also. Okay, even when you do a x bar equal to w into x bar, this also will have 4n square multiplications. This is about the real multiplications. Okay, and you will have n into 4n minus 2 additions. Okay, yeah. So this was about the complex, considering that there's a that x is complex, x of n is complex number, and you know that wkn of n is again a complex number, right? So if I the whole calculations here were all real multiplications, because we had separated complex number as in the form of a plus jb, and this in terms of j plus c plus jd, and when you calculate the real multiplications will be ac, ad, bc and bd, right? So this will be the real multiplication. So on a whole, if given the formula of x of k equal to summation n equal to 0 to n minus 1 x of n into wkn of n, if both the numbers are complex, then we saw that you need 4n square real multiplications, or you need n complex multiplications for one value of multiplication for one value of k, right? So such that for n point DFT, for n calculating n values of DFT, you will need n square complex multiplications. Okay, complex multiplications. You know that the every one complex multiplication has got like 4, right? 4 because this is 1, a plus jb into c plus jd is one complex multiplication. That turns out to be 4 real multiplications involved in that process. Okay, so same way there is like n minus 1 complex additions for one value of k. For n point DFT, there will be n into n minus 1 additions involved. Okay, complex additions involved. Okay, so that's how we this is the basis for having a better FFT algorithm. So this, if we think about it, like let's say if you want to calculate a 64 point DFT, right, it's basically 64 square complex multiplications involved, right? 64 square is 2 raised to 6 into 2 raised to 6, which is 2 raised to 12. So 2 raised to 12 is like 4096 complex multiplications. So every complex multiplication involves 4 multiplication sub multiplications. So it's actually 4 into 2 raised to 12, which is like 2 raised to 14, which is 16 how much it is, 16384 multiplications to calculate, just to calculate a 64 point DFT, and so many, 64 into 63 complex additions. Okay, so on. So that's quite a sizable number. If you go about it like because the number actually x of n can be a floating point number. So if it was an integer multiplication, that's okay, but this is like floating point operation I am talking about. The floating point operations are complex. Complex meaning time consuming. So that's why when you have time consuming operations, so that's why this is like a big deal. You need to reduce this for you to get a faster calculation. Okay, now